Okay, it's 8 a.m. and so let's start this class. And the major goal of this class will be magnetic force. So we need to introduce this very important quantity, very important quantity, right? Okay, so but before I introduce this magnetic force, let me discuss one important observation, although it's called Ørsted experiment. It was observed at the beginning of the 19th century by Ørsted, right? And according to the history, right, according to the rumors, he was running some demonstration. He was an instructor, and he had a long wire, and he ran a large value of the current through that wire. And by accident, there was a compass nearby, right? So, and he noticed, yeah, and he noticed that whenever he turned on the current or turn it off, the compass needle responded. It started turning, right? It sounds like so banal, so simple, right? Right? But nevertheless, lots of researchers believe that this was one of the most important experiments ever done. What's so special, what's so important about this observation? Right, I even cannot squeeze out of my cell experiment. Yeah, it's still experiment, right? But looks like an observation. And the thing is, all right, up to this point, okay, up to that point when he ran this experiment, researchers were divided kind of in two groups, right? Who worked some of them worked in the world of electricity. So that was their playground. They thought that this is their independent world. So that's where they had their fun. Some researchers worked in the world of magnetism, right? And they thought that these two worlds kind of independent, right? So they played, they had their own fun in the with the magnetism, right? And what do we have in this experiment? So we have current, a pure representative from the world of electricity, and compass needle, basically a permanent magnet, pure representative from the world of magnetism. And they interact. It means what? It means if they interact, it means that these two worlds, world of electricity and world of magnetism, are not that independent. They actually overlap. It's a clear indication that these two worlds overlap. Of course, they didn't know how deep overlapping is, right? Of course, now we know that they're both almost inseparable. They're almost inseparable, right? But back then it wasn't obvious. And as a result, so after this demonstration, he showed that yeah, these two worlds overlap. It triggered lots of additional research, right? Lots of new people dived into this world of electricity and magnetism, like Ampere, I know Faraday, then later Maxwell, right? And it triggered a significant amount of great results because of this simple demonstration, right? People realize that there are tons of potentials in this direction. Basically, now we can say in the direction of electromagnetism, right? So that's what so important about this experiment demonstration, right? And that's why every time I like discussing this, right? I like talking about this, right? Okay, so and now after this we can yeah. Actually, yeah, another thing I wanted to mention. It's not the end basically of the story. Of course, soon people realize that basically world of electricity and magnetism inseparable. They create a world of electromagnetism, but even worse, right? At some point, this world of electromagnetism annexed the world of optics. Up to a certain point, right, optics was the separate world, completely independent. And after Maxwell managed to write all his Maxwell's equations, right, he showed that optics is just a world where electromagnetism applied all or most of its laws, right? So optics is just an application of electromagnetism, right? So strictly speaking, optics is also part of electromagnetism. But of course, it would be much later, right? After this demonstration. Okay, enough of this history, and back to the new material, right? So what we've achieved in the world of magnetism up to this point. So we introduced two fundamental laws, universal laws, right? So now we know how we can find magnetic fields, right? And we know two methods of finding magnetic field. You can use either Biot-Savart law, right? Or Ampere's law. So now we have pretty much all ways of finding magnetic field. So then what else do we need in order to have foundation, almost complete foundation of magnetism? And similar we've done in the world of electricity. So what else now do we need to introduce in the world of magnetism? Of course, now we know how to describe magnetic field production. But of course, then the next logical question, how do these magnetic fields interact with materials, objects, right? And which quantity do we usually introduce to describe interactions? Force. And since this force is going to have magnetic nature, so it makes sense to call it magnetic force. So now the next natural step, or okay, not obvious, but natural step should be we need to introduce magnetic force. And of course, the fundamental equation expression for the magnetic force. And if basically you know how to describe interactions of a magnetic field with a point charge, right, with a point charge, then if you know this expression or formula, you should be able to describe interactions of magnetic field with any other complicated object. Of course, you can apply some maybe complicated logic, right? But it can be done. Once you know expression for a magnetic force on a point charge, then using some logic, you should be able to describe interactions of magnetic field with any other objects, right? So the fundamental equation will be magnetic force on a moving charge, right? And you see, charge must be moving in order to have magnetic force, but we will see in a second, right? So basically, this expression for the magnetic force and these ways of finding magnetic field, they form the foundation of magnetism, but not completely. We will see what else can be added. Okay, so that's what we need to introduce today. And then what if you have not just a one point charge moving? What if you have a bunch of identical charges drifting in the same direction, which is the current, right? Which is the current. So of course we should be able to make a transition easily from this formula to the next one, magnetic force on a current. But of course you need to realize that this is the fundamental equation, right? Which cannot be derived, which was written based on observations, and which will be added to the set of Maxwell's equations. This equation will be added. Not that. This is basically very practical, very useful. Most of the time in our life, of course, we use this maybe formula. But still, this is the fundamental one, the foundation. Right? Okay, so anyway, we need to introduce both of them, right? But I just wanted to make a point that this formula, of course, can be derived from that. And this is the foundation. Right? Okay. Right, and of course, very similar steps we've done in the world of electricity. We introduced two formulas which can be used to find electric field, and then we added expression for the electric force, and now we are sort of repeating steps, but of course in the different world, in the world of magnetism. Right. Okay, so now let's introduce this magnetic force on a moving charge. Okay, so let's assume that we have some, for example, positive charge Q, which flies or moves that way with velocity v. Of course, it must be exposed to some magnetic field. And let's assume at this particular point, magnetic field points that way. So that's our magnetic field. And so at this point, nothing else I can say except for sort of here's the formula and let's use it. And yeah, because it's a fundamental equation, basically it's taking as an axiom, right? Written based on observations, right? So, of course, I should add here some kind of key music, right? I'm still thinking about this, but haven't done it. So we have a force acting on a charge equals the value of the charge, and charge can be positive, can be negative, remember, right? And then the cross product, again, as I told you a few classes ago, from now on, lots of formulas are going to have the cross product. Here's another example. Cross product between the velocity of the charge and the magnetic field to which charge is exposed, V cross B, right? And of course, you see, all the time, this force, magnetic force, must be perpendicular to the velocity of the charge and the magnetic field. Right? And so now how can we find it? Of course, usually we're going to divide the process of finding a magnetic force into two steps. Magnitude of Q, magnitude of P, magnitude of B, and times sine of angle between them, right? So it can be, not it can be, it is this angle alpha. This is the correct angle between these two vectors, V and B, right? And direction, of course, in order to find the direction, you need to apply right-hand rule number 1, which we use to find direction of the cross product. Basically, finding a direction of magnetic force is in this cross product, but it's not complete, but it's not it's not the whole story. It's not the whole story. Look, basically here, the process of finding a direction of the magnetic force consists sort of like out of 1.5 steps. First, yeah, you apply right-hand rule for this cross product, V cross B, right? Align your hand along V direction, then bend your fingers towards along the first along V, then bend your fingers along B direction, and then your outstretched thumb gives you direction of V cross B. But it's only first step. Second, sort of like a half a step, you need to have a very quick look at the sign of the charge. If the charge is positive, then of course direction of the cross product gives you direction of the magnetic force. But if this charge is negative, then once you found the direction of the cross product, you need to flip that direction. Quite often, okay, not quite often, but I see sometimes students forget about that. But I will keep reminding you about this for the next couple of weeks, right? So don't forget, so every time, 1.5 step. First V cross B, and then adjust if it's needed, adjust the direction if it's needed because of the sign of the charge Q. Right? So again, force, in this case magnetic force, is sensitive to the sign of a charge. The same we had with the electric force, right? You remember I told you about that. Okay, so now in this case, V cross B. So V that way, B, so I have to bend my fingers that way in the direction of the magnetic field, and then my thumb gives me direction of the cross product. It's a up. And then quick look at the sign of the charge. Charge is positive, so that direction is the correct direction for the magnetic force. So that's the direction of the force. But if we had a negative charge, the force F would be downward. We would flip that direction. Okay, so that's the, and quite often it's called Lorentz force, right? Lorentz force. And again, I emphasize it's a fundamental equation. You can apply it, basically no limitations. You can apply it at any point of the universe, at any point of time. Anyone can do that, right? Okay, so now let's look at a few examples. Okay, so I just copied and paste the formula. And let's say we have a charge, you see positive charge, moves along the magnetic field lines. Here, what I wanted to also mention, right, I forgot. You remember a few classes ago, I told you that everything in the world of magnetism is in dynamics, right? You remember, in order to produce magnetic field, a charge must move in a Biot-Savart law. You remember the force, the velocity is involved, right? So if a charge is stationary, it cannot produce magnetic field. Now the same similar story with the magnetic force. Again, you see velocity is involved in this formula. So in order for a charge to experience magnetic force, it must move. All right, charge must fly. If you have a stationary charge exposed to a magnetic field, it is not going to experience magnetic force. So the charge must be in dynamics. It must move. Only then, yeah, it will experience magnetic force. Right? It's a nice world, magnetism. You have to move in order to do something. It's like in real life, right? Okay, so back to this example. All right, so basically it's sort of a situation if you take for example, solenoid. You remember it produces uniform magnetic field inside, and magnetic field lines are parallel to the axis of the solenoid. So what if you shoot charged particle through the axis of, along the axis of the solenoid, right? So what can you say about the magnetic force in this case, in this situation? Okay, let's look at the magnitude. You remember it's a q v b times sine of angle between those two vectors, vector v and vector b. But in this case, what's the value of the angle between v and b? 0 degrees, because they are parallel to each other, right? These two vectors parallel, so 0 degrees, sine of 0 degrees is 0. So in this case, this charge is not going to experience force. The magnetic force is 0. So magnetic force is 0. In this case, of course, we cannot talk about the direction. Right. So in this case, if you shoot the particle along the axis of the solenoid, that particle is going to fly along straight line with the constant speed forever, in the same direction forever and ever. So we're going to have a uniform translational motion. In this case, since the magnetic force is 0. Okay, so now let's make situation slightly more complicated. Let's turn this magnetic field by 90 degrees. And, change direction of the velocity. Okay, let's change direction of the velocity. Right now, it is perpendicular to the magnetic field. So, what's the direction of the magnetic force in this case? Right. So, cross product V. First, I need to align my hand like this, right? Then bend my fingers towards the second vector in the cross product B, and as a result, my outstretched thumb gives me direction of the cross product. So it's a first step. We looked at V cross B, and then we need to look at the sign of the charge. Since charge is positive, so that is a correct direction for the magnetic force. If charge were negative, of course I would flip the direction, and it would be out of the screen. But in this case, since the charge is positive, magnetic force is into the screen, into the page. Okay. Right, so you see, we need the right-hand rule, right? Almost every class now. Right. So now, what if we have this situation? So you see, magnetic field is into the board. You see a bunch of crosses, and positive charge flies this way. Again, so what's the direction of the force? In this case, velocity and B are not parallel, so magnetic force is not going to be 0. Let's find the direction. Again, first align your hand along the direction of V, so it's this way. Then I need to bend my fingers towards the second vector in the cross product, right? So that vector is into the board, into the screen. So that's the correct position of my hand. And my outstretched thumb gives me direction of the force. it's a first step, and the second step, look at the sign of the charge. Charge is positive, this is the correct direction for the magnetic force. Again, if the charge were negative, force would be downward. Right. But in this case, since the charge is positive, so the force is up. Right. Okay, and the last example. What if we have this situation? Again, magnetic field is into the board, and now negative charge flies this way. So what's the direction of the magnetic force acting on this charge? Again, first the cross product V cross B. V cross B. So direction of the cross product is up, but now our charge is negative. So we need to flip that direction. So the magnetic force will be downward, right? And of course, this charge will fly kind of downward, right, slightly. So some parabolic motion will be more complicated trajectory. So, but anyway, the in this case, magnetic force points down. Okay, and now a couple of questions for you. All right, it's in the chat. I created new 2 new polls, right? Right after midnight, so you don't have to scroll much up. Okay, let me open your chat. Okay, yeah, it's right there. So it's number 1, March the 30th. Right. So what do we have? You see, magnetic field lines, you see them? They are created by this permanent magnet, right? And there is a charge, positive charge, flying up. So what's the direction of the magnetic force acting on this positive charge? In this case, actually, it's a proton, right? So, and you see 5 options. Right? And of course, I posted the formula for the magnetic force, Lorentz force. Okay, give it a try. Where are the results? Okay, I see. Started answering. It's again, it's a question 1, because there are 2 questions. Okay, I see. 1 student answered the second one. You can still change it. Forgot to turn on timer. Okay, it looks like we almost reached the maximum. Number of responses are not growing. Okay, so now let me discuss it. Okay, cancel it. So it's quite simple. We just need to, first of all, I need to see direction of the magnetic field, B, right? So, of course, the direction of the magnetic field, it's a tangent to magnetic field lines. Since at the point where the charge is magnetic field lines, direction is that way, right? So magnetic field will be also that way. So I can show it. I need to press on slides. Yeah. Okay, so that will be the direction of the magnetic field. So now right-hand rule, and then since charge is positive, direction of the cross product is going to give us direction of the magnetic force. All right, so V cross B. So my thumb gives me a force which is out of the screen, out of the board, right? So the answer, yeah, that's correct. And let me check your answers. Okay, great. So 95%, it's nice. Right? If you still need, if some of you are still not comfortable with the right-hand rule, come to office hours, right? We can practice that. It's quite simple, right? Okay, good. Now, in this case, the same question. What can you say about the magnetic force in this case? So again, you see magnetic field lines, you see the electron traveling towards me. All right. So what can you say about the magnetic force on this electron? And you see directions, and the last option, the magnetic field is 0. Okay, so now let me answer. Actually, it's quite straightforward, right? So again, so we just need to see direction of the magnetic field. Of course, it will be towards the magnet, right? Because that's the direction of the magnetic field lines, right? And magnetic field is tangent to magnetic field lines, so it will be this will be a direction of B. So now cross product of two anti-parallel vectors pointing in opposite directions. The angle between them is 180 degrees. Sine of 180 degrees is 0, right? So I just discussed the absolute value of the cross product. QVP sine of 180 degrees. So in this case, the force is 0. So it means that this electron is going to fly in the same direction. Towards me, right? This way. In the same direction with the same speed forever and ever. So it is not going to experience the magnetic force. So most of you answered right. Option D, the magnetic force is 0. So now, next. So the previous, it was the fundamental equation. Now the next one, it's not a fundamental equation, but very practical, right? Because most of the time in our life we deal with currents, right? Not just point charges. And as I said, the transition from the mathematical point of view is quite straightforward, but still we're not going to do it. We will just present the next formula and we will start using it, right? Okay, so let's assume that we have a completely arbitrary piece of wire with a current. Let's assume current flows that way, so that's our current I. Right. And our fundamental equation, which we just, of course, it must be exposed to the magnetic field, right, naturally, right, in order to have a magnetic force. And of course, we need to start from this fundamental equation, right? Q, V cross B, it's a force on the point charge. And of course, as I said, like using reasonably simple math, you can make a transition from this formula to the formula which describes magnetic force acting on the wire. But we cannot write down the formula for the whole wire of an arbitrary shape, because different pieces of wire are under different conditions, right? Somewhere magnetic field can be stronger, weaker, right? At some points, pieces of wire can point this way, some places that way, right? So as a result, we should write only the expression for the magnetic force acting on infinitesimally short piece of wire, right? Sort of like if we take this, right? And of course, some of you might expect up to this point, the book all the time used the symbol ds for infinitesimally short section of the wire. But now, the author switched to dl. And the reason is quite simple, right? Because you can open any book, right? Any book in physics. It's sort of like an unwritten convention. Every book uses dl in the formula which we are going to introduce, right? So sometimes I feel like, and like the author of this book, there are some classic books, right? And some other people try to publish their own books, and they try to use different notations quite often. Sometimes maybe not the most convenient notation, but they try to be different. And I feel like in the case of our book, also the author wanted to be different, and he used ds all the time. But when he came to this point, And it's sort of like an unwritten convention. Everyone uses DL. So he switched from DS to DL. It's not a crime, but it doesn't sound cool, right? When you, in the same book, changes notations for the same thing, right? If you started using, no, using DS, okay, stay with DS till the end, right? But okay, again, it's not a big deal. You can easily adjust yourself. So just be aware. So now instead of DS, book uses DL, right? And you see, we present it as a vector. And again, what determines direction of DL? Current. Direction of the current give us direction of DL. Right. Okay, so now after reasonably simple math, you can make a transition from this formula to this formula, right? And you see they're they're kind of similar. And you see now it's a force on this short section of the wire. And it is equal I and cross product between DL and B. So now, if you want to know the direction of DF, here you have now you have to make only one step. You just need to apply a right-hand rule for this cross product, because I, it's a magnitude value of the current, current here cannot be negative. It's only positive number, right? So here DL cross B gives you direction of the magnetic force immediately. But in this fundamental equation, it's a 1.5 step. First V cross B, and then adjust if it's needed based on the sign of the charge, right? Okay, so this is the magnetic force on the segment DL. But we're not going to use, I think we're not going to use this formula. We're going to use sort of simplified, this formula applied for a straight wire with current. Right? Of course, this formula can be applied for any wire, any bent in any way, right? Twisted in any way, you can apply this formula. And also it can be applied for a straight wire which is exposed to the magnetic field. We're going to use the next formula. Right. So if you do that, if you apply, and the transition is very simple. Plus, we're going to assume that this straight, okay, here, this straight wire with current is exposed to a uniform magnetic field. Right. So what if B is constant? In this case, integration, of course, you have to integrate it. By integration will be trivial. I is constant, B is constant. You just need to integrate DL, and it will give you the length of the wire, which is exposed to the magnetic field. So transition is trivial, banal. So as a result, we can write the formula, which gives us a magnetic force acting on a straight wire with the current I, and which is exposed to a uniform magnetic field B. And the formula will be F equals IL cross B. That's what we're going to use in this semester quite often. Again, for a force acting on a straight wire with current A and length L, and exposed to the magnetic field B. Right. Again, this is a fundamental formula. This is not. Right. Again, this can be derived. Okay, so now let's look at a few examples. And the next recitation class, we will spend plenty of time playing with this formula. Right. Yeah, the first example. So what if we have a magnetic field? You see direction of the magnetic field straight up, and current also flows up along this magnetic along this wire. So what can you say about the magnetic force acting on this wire? So we can apply that formula. It's a straight piece of wire, right? So we can use the last formula which we introduced, IL cross B. Right? Again, direction of L is determined by the direction of the current. Okay, so in this case, L, you see, current is up, so L is up, right? And magnetic field is also up. So those two vectors are parallel to each other. And what's the value of the cross product of two parallel vectors? 0. Because it's what? It's a L times B times sine of angle between these two vectors. And since the angle is 0, sine of 0 degrees is 0. So magnetic force acting on this wire will be 0. So no magnetic force. All right, so as a result, this wire is not going to be bent in any direction. Right. Okay, so next example. What if we turn this magnetic field by 90 degrees? Of course, now the angle is not going to be 0 degrees, and of course, this wire is going to experience a non-zero magnetic force. Right? So, and this picture actually shows immediately the direction of the magnetic force, but let's actually get it. So, current still up, right? So, L direction is up. Magnetic field is into the page. You see, process means into the page, into the board, into the screen. And so now apply right hand rule. So first L, I align my hand along L direction, right? And then I need to position my hand like this so I can naturally bend my fingers towards into the screen. That's the B direction, right? So L cross B, and my thumb gives me direction of the force. And again, in this case, we have to make only one step, right? Right hand rule number 1, because again, the value of the current can be only positive. So L cross B give us a correct direction of the magnetic force. Right? So in this case, wire will be bent, of course, towards me. Right? So you see, it's quite straightforward again, but you have to be very comfortable with the right hand rule, because now almost every formula, in every formula, you need to use the right hand rule, number 1. But based on the first clicker question, I feel confident that you are capable of doing this. Okay, so now sort of summary. So you remember, as I told you, in the world of electricity, we first introduced, in order to lay down the foundation of the world of electricity, first we introduced two ways of finding electric field: Coulomb's law with the probe charge, or we could use Gauss's law. And once we added electric force expression for the electric force, again, that is one of the fundamental equations. So basically, this was our foundation in the world of electricity. And now we introduce something similar in the world of magnetism. So basically, I can almost say we lay down the foundation, because in the next classes we will see that something is still missing, but we will discuss that later. But for now, it's almost the foundation. So now we introduce Biot-Savart law and Ampere's law. They can be used to find magnetic fields. It's like here, where these are used. We're used to find the electric field. And then we introduce now the magnetic force, which describes interactions of these fields with point charge. Right. So this, up to this point, this we can say for now it's a foundation of the world of magnetism. Of course, the last equation is not a fundamental equation. It can be easily derived from this one. Right. And we will see when we get to the point when we finally introduce the whole set of Maxwell's equations. So we will present nicely Maxwell's equations, and we will add this equation, right, electric force and magnetic force, to that set of equations in order to have a complete foundation of electromagnetism. Right? Okay, so now let's look at some applications of this fundamental formula. Very cool, very beautiful application. Let's introduce what is called cyclotron motion. All right. So what is that? We will see. Not that complicated, but leads to a beautiful results, really amazing results. Right? Phenomena, not results, phenomena. Okay, all right, so these are sections. And so we just discussed, if you, for example, let's say magnetic field created by a solenoid, right? And of course, magnetic field lines are parallel to the axis of the solenoid. And if you take a charge, point charge. And if you shoved it, if you send it through the axis of the solenoid, in that case, magnetic force will be equals to 0, right? We discussed that a few slides ago, because in that case, velocity will be parallel to the magnetic field, right? And in this case, magnetic force equals 0, and the charge is going to fly along a straight line forever and ever, right, with the same speed and the same direction, because again, as I said, magnetic force will be equal to 0. But what if we, I don't know, drill a hole in the solenoid and send the particle perpendicular to the magnetic field, perpendicular to the magnetic field lines? What are we going to observe in this case? And of course, it will lead to this cyclotron motion. Again, so first, in the case, if you send the particle along the magnetic field lines, it's a boring situation. It will just, it just leads to a uniform translational motion. But if you turn direction of the velocity by 90 degrees, it will lead to this interesting phenomena. So let's discuss that. So let's assume that we have this magnetic field, right? You see, it's a uniform magnetic field, and it points into the screen, right? And as I said, we want to send particle perpendicular to this magnetic field. Oh, for example, let's say it's a positively charged particle for simplicity, and let's assume it moves this way at this particular moment of time. And first, let's discuss which trajectory, first conceptually, which trajectory are we going to observe in this case? So first of all, of course, in order to get the idea of a trajectory, we need to see direction of the magnetic force acting on this charge. Without force, we wouldn't be able to answer this question, right? So let's get the direction. And we can easily get that because just now we introduced the fundamental formula, QV cross B. Charge is positive, so direction of the force is given by the cross product, V cross B. Okay, so right-hand rule, V, so that's the direction of the V. Then I have to bend my fingers towards the second sector and the cross product into the screen, and my thumb gives me the correct direction, right? So that's the direction of the force. And of course, as I told you already several times, force is perpendicular to the direction of the velocity all the time. And that's what we have, right? V that way, and magnetic force is perpendicular. So now, which trajectory? All right, force all the time leads to acceleration, right? Newton's second law, F equals ma. If there is a force, there must be acceleration. And acceleration all the time describes what? Changes in the velocity. Accelerations all the time, an acceleration all the time describes changes in the velocity. It means that force changes something in the velocity. What does this force change in our velocity? Does it change its magnitude? No way, because this force acts perpendicular to the direction of the velocity. So this force cannot change magnitude of the velocity. So it means that we're going to have a constant speed of this particle. So we're going to have some kind of uniform motion. Uniform, it means with a constant speed. Magnitude of the velocity stays the same. So this force cannot change magnitude of the velocity. Then what does this force change in our velocity? So let's say this is our velocity, this is our force. This force acts perpendicular to the velocity, and what it changes direction. It, of course, particle tries to fly over a short period of time, and over that infinitesimally short period of time, this force changes its direction, right? And once velocity changes its direction, of course, force also changes its direction, because all the time force is perpendicular to the velocity. It doesn't matter what's the direction of the velocity, force will be all the time perpendicular. So first, over first small dt, right, this force changes direction of the velocity slightly. Then again, particle tries to fly, right? Okay, flies slightly, right? And the force changes its direction. Then again, 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 right? So what are we getting? You've seen this motion in physics 1 when the force was perpendicular to the direction of the velocity. You remember orbital motion of some satellites around the Earth? It's exactly the same here. We are going to get a circular motion. Circular motion. Where is it? Here. Circular motion. All right. And of course, this force, which is perpendicular to the velocity, it leads to a certain acceleration, special acceleration, right? And you remember that, right? Some of you remember. Centripetal acceleration, right? And you remember from physics 1, if somebody tells you, okay, I have a trajectory and centripetal acceleration is, I don't know, blah, 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 5 meters per square seconds, it should tell you immediately that that trajectory is circular. Or if somebody tells you that I have a circular motion, it should tell you immediately that it has a non-zero centripetal acceleration. Circular motion and centripetal acceleration are inseparable all the time, right? So in this case, of course, we are going to have centripetal. So this force is going to give us centripetal acceleration, right? Okay, and of course, yeah, as I said, if, for example, velocity, particle is over here, velocity this way, but force is still perpendicular. Or here, right, the same. Velocity that way, but force is still perpendicular. So this type of motion is called a cyclotron motion. Right. Okay, so right now, we discuss it sort of conceptually. Now, let's describe this trajectory. Let's apply some equations, like, since we are all science majors here, so of course at the end of the day we must apply some equations, derive something so that we can get some numbers and so on, right? Conceptually it's fun, it's nice, but it's usually the first step, right, in the process. Right? And what does it mean to describe this trajectory? It's a circular motion, right? Circular motion. If you know radius of this circle, right? You can say you know everything about this trajectory. So effectively, we just need to find the radius of this trajectory. It's called cyclotron radius. Right? It sounds so cool, cyclotron, right? But in by the meaning, it's reasonably straightforward, reasonably simple process. But sounds very cool, cyclotron, right? Okay, we still have a couple of minutes. Okay, so now let's try to derive cyclotron radius. Okay, so let me just reproduce the picture. So we have this uniform magnetic field, velocity, right, force perpendicular, right, and this is trajectory. And as I said, that's what we will have to eventually find, cyclotron radius, right? And you remember in physics 1, which axis did you use to describe a circular motion in this book? Right? Instead of x and y, we use different axes. We used what? T, which gives us a tangential direction, and okay, here T, right? Tangential direction, and R, radial direction. Right. Okay, pretty much. Okay, so yeah, the class is over. Let me just quickly say a few words what we're going to do. So pretty much now we will have to apply Newton's second law for both of these directions, for direction T and for the direction R. In the T direction, you see, we don't have any forces acting. The force is only in the radial direction. You see this, this magnetic force. So if there is no force in the tangential direction, of course, it will lead us to the important piece of information that the speed of particle is constant and we are going to have uniform motion, right? But of course, we are going to get information about the cyclotron radius when we apply Newton's second law in the r direction. And of course, acceleration in this direction is the centripetal acceleration. So we'll just equate ma centripetal acceleration equals to the value of this force, right? And from there, we will get the expression for the cyclotron radius. Okay, so most likely, since next class is the exam, this discussion of the cyclotron radius, the rest will be done in our recitation classes, right? So we will just derive this, we'll just reproduce this picture and derive the expression for the cyclotron radius, and it's reasonably straightforward. And we will solve a few problems.